Hey everyone, Radzien here. In this video, we'll walk through building a simple cryptocurrency trader using TypeScript. To streamline the development process, we'll leverage RadzionKit, a TypeScript monorepo boilerplate, as our foundation. We will implement an automated moving average crossover strategy where the bot runs every 10 minutes and uses a short-term period of 20 and a long-term period of 50 to identify buy or sell signals based on trend changes in the market. The state of our trader will include an ID for referencing the state in the database, prices to store the historical prices of the asset up to 50 based on our configuration, the asset we are currently trading, and the type of the most recent trade. To minimize fees, we'll use Polygon, a layer 2 scaling solution for Ethereum. We'll store the state of our bot in a DynamoDB table. Using utilities from RadzionKit, we can quickly define the essential functions needed for basic create, read, update, and delete operations. To ensure type-safe access to environment variables, we'll use the getEnvVar utility. This will act as a single source of truth for managing our application's environment variables. We can populate the database with initial data using the setTrader script. Since this script is only for our use, it's safe to delete all existing traders before adding new ones. Currently, our system supports only a single trader, as it trades the entire amount of the asset. However, it can be easily extended to support multiple traders handling different assets, such as wrapped Bitcoin. Even though we haven't made a trade yet, we still need to set the last trade field to align the bot's actions with the deposited asset. This should be buy if you deposited USDC into the account, so the bot can buy wrapped ETH on a signal, or sell if you deposited wrapped ETH, so that the bot can sell it on a signal. To keep track of our bot's activity, we'll set up Telegram notifications for trades. Whenever the bot makes a trade, it will send a message detailing the action, the asset, and the price. This provides real-time updates, ensuring you're always aware of the bot's decision without manually checking logs. To improve security, we'll store sensitive information such as the Telegram bot token in AWS Secrets Manager. This approach centralizes all secrets required by our service. To optimize performance, we'll minimize the getSecrets function to cache the response, reducing the need for repeated requests. The JSON response is then parsed and we assert the specific field we need. To fetch cryptocurrency prices, we use the CoinGecko API. The getAssetPrices function accepts an array of asset IDs and an optional fiat currency. If we were trading wrapped ETH against wrapped Bitcoin, this approach wouldn't work. In that case, we would need to query a swap code and derive the price from it. However, since we are trading with stable coins, we can rely on the direct price from the CoinGecko API. To enhance security, we'll avoid storing our primary wallet's private key on the server. Instead, we'll create a dedicated account solely for executing swaps. This account will hold only the asset we want to swap and a small amount of pool to cover gas fees. A simple script will generate a private key using VM and derive an account address from it. Once our trading activities are complete, we'll use the withdraw function to transfer all remaining assets back to our primary account. The withdraw function iterates over every supported asset, checks the balance, and transfers the entire amount to the specified address. The getERC20 balance and transfer ERC20 token functions handle this process by interacting with the ERC20 contract methods to read balances and transfer tokens, respectively. To execute a swap, we'll leverage the 0xSwap API, which identifies the optimal route for the trade. We are using Permit2 because it simplifies and streamlines token approvals for different protocols. Instead of needing multiple transactions and approvals, Permit2 consolidates the steps with a single signature, reducing gas costs and making the swap process faster and more straightforward. We check if there is an allowance issue in the code because smart contracts need permission to transfer tokens on your behalf. If you haven't already approved the contract to move your tokens, we must set the token allowance so the swap can succeed. This extra step ensures the swap contract has the necessary access, preventing transaction failures due to insufficient allowance. we appended the EIP712 signature to the transaction data so the contract can verify that you've granted permission for permit 2. By signing the type data first and then adding the signature along with its length to the transaction, the on-chain contract can confirm it's authorized to move your tokens according to the permit 2 specification, all in a single seamless step. The transaction generated from the code already includes all the necessary fields. Our task is to convert specific fields, add appropriate types, and include the nonce before sending the transaction. To ensure the transaction is successful before proceeding, we use the assert transaction function to wait for the transaction received. If the transaction fails, an error is thrown with the transaction status. Every 10 minutes, we will execute the run traders function. This function begins by updating the prices of the assets, filters out traders that lack sufficient historical data, and finally run the trading logic for each eligible trader. To update the prices of traded assets, we fetch the state of each trader, then retrieve the prices for all assets being traded. Afterward, we iterate over each trader, updating their historical prices with the latest data while limiting the array to the long-term period defined in the configuration. This ensures the bot maintains an accurate and manageable history of asset prices for its trading logic. The runTrader function executes the trading logic for a single trader. It calculates the short-term and long-term moving averages of the asset's historical prices to determine a trading signal, either buy or sell. If the short-term average crosses above or below the long-term average and the signal differs from the last executed trade, a transaction is triggered. The function retrieves the trader's private key, determines the appropriate assets to swap, and executes the trade using the 0x-swap API. After completing the trade, it sends a Telegram notification with the trade details and updates the trader's state in the database, including the new last trade value. We'll deploy our code as an AWS Lambda function, roping it with Sentry to receive notifications about any potential issues. To provision the necessary AWS resources for our services, we will use Terraform. To ensure the function runs every 10 minutes, we'll configure a CloudWatch Event Rule. The Terraform code for the setup is available in the description below. By combining TypeScript, AWS, and powerful APIs like 0x and CoinGecko, we've built a secure, efficient cryptocurrency trading board. That's all. Explore the repository linked in the description to dive deeper and start building your own trading board. See you next time.